Hello and welcome everyone. So now we were discussing about loss functions in the previous lectures. So now we sort of wrapped up about loss functions. We said that this is a function which quantifies how much better or how much good your model is. Now we'll have to perform backpropagation. So that will be the title of the lecture, backpropagation. But I'll just give you the big picture. So we had data that we haven't learned much about. So because we need to encode data, and there is a lot to learn about data. We will have to see how can we encode textual data, how can we encode speech data, how can we encode images. So there is a lot to learn in this. After this we had model. So in this model we are now in the model we selected is neural network, and we'll change different architectures of this. And I gave you a brief summary of what a neural network looks like. Okay, not just maybe more than a brief summary. And then we were in the learning thing. So in this learning we said we'll use gradient descent to learn. So this will be the learning algorithm. Okay, gradient descent, we have to compute gradients of something, and then we'll have to move in a certain direction, and we'll use this gradient descent to update our parameters. And we'll have to see how to find these gradients. So these gradients are to be found somehow. So if we are given a network, and then you know that I'll perform something, and then I have to adjust these parameters, I have to adjust these weights and biases. So how to adjust now? So we have to find gradient for that. And how to find this gradient? That's why we'll come to backward pass our backpropagation. This is going to be one of the important lectures in whole deep learning. If you understand backpropagation, you are understanding heart of deep learning. Okay, this I can consider the heart of deep learning, backpropagation. If you understand this, because of this backpropagation algorithm, that's why deep learning took the turn it is. It took maybe 20 years back or 15 years back, and you are seeing it in some state today. This was because of backpropagation. It was discovered way earlier, but we didn't have any method to any sort of good hardware to implement it at scale. So that this was made possible by backpropagation. Okay, let's now see. Let's again do a bit of revision about how the network was. So we had a neural network in which we had some input layer, and then we had some hidden layers, and after that we had an output layer. Okay, I hate to make this again and again, but no choice. Okay, so let's suppose this is our input layer, and let's suppose now we have some hidden layers over here. I can use this throughout the class. These are some more hidden layers. Okay, and suppose we can have more hidden layers like this, and we'll have an output layer from which we'll get an output. Okay, if somebody of you remembers the notation, so what we did is we said we'll represent these WK matrices. These WK matrices will be the matrices that will be in the middle of these layers, because this is we have connections between these layers, so that for each of the layer we have this WK matrix, and for this each of this will be by weight something of this sort, W, K, I, and J. Okay, we have matrix of this sort. I think if you see some previous lecture, you will find that notation, you will find those notations. And then we also have biases. So bias will be something represent like this, B of K of I, let's suppose. So this will be telling you the ith bias. And then in the middle we said before this we had pre-activation. So you had aggregation or activation function, so we wrote it something like this. So this aggregation function was represented by A, and then after you activate something it was represented by H. Okay, so this is the notation that we had. So I'll just write them down. So these were your weights, and these are your biases, and then we had AK was the pre-activation values. And then we had HK were hidden activations. So these were like we had linear layers because we did affine transformation, and then we have to activate these things, and then that's how we wrote H and K. And H of 0 was our input. So this was our input. Okay, and output was written by H of L. This was output. So this is just summarized notations that we earlier covered in one of the lectures. Again, to tell you, these will be notations we'll be using throughout. So math might look a little messy. That's why I am refocusing on these notations much. So this WK will be the weight matrix. So what is this K? So this is the layer which will be connecting K minus 1 and Kth layer. Okay, and if I write IJ, so IJ, this will be the source neuron, and this will be destination. This is source and destination, or source is sink. And we usually do it in reverse. And then we have this B of K. Again, this K this is the kth layer, the bias for the neuron I in the kth layer, and then we have this AK. So AK is a pre-activation layer, and HK is the hidden activation layer. And now we'll do how is the forward pass done. Okay, I'll just write the forward pass. Now based on how can we do forward pass, the only difference can lie in the last layer where we apply these last activation functions. Okay, so I have given you the rationale behind that. So if I, let's suppose, take any layer K can be 1, 2, 3, let's suppose till L, if we have L layers in our network. So if I take AK, activation of a layer AK, so this is our aggregation, so this is non-linearity rather, so affine transformation. You will take WK, you will take the matrix corresponding to that, and HK minus 1. Okay, and then you'll add the bias K towards it. This is the equation we also wrote in the previous session somewhere. So this is the aggregation function that you do, or this is the linear transformation or affine transformation. This is the first step in the forward pass. You will be given, let's suppose, something, if you have to calculate AK of this, so you will take weight matrix corresponding to the kth layer, basically the layer which is having K minus 1 and K, so it will be between that, and then you will have this hidden layer HK minus 1, and you will add bias to this. And then after you have this, you will have to apply activation. Consider this is activation. F of K is the activation. Let me also write that over here. So consider this F of K. So this is activation function of layer K and K minus 1, where we apply this activation. So I can write this F of K like this, F of K, and then this will take input AK, and this will give you the hidden output. So this should be giving you the hidden output. So H of K, so I am writing K rather. So H of K is F of K and A of K. So this over here is application of non-linearity. So non-linear activation. Okay, so this is how you do the forward pass. So if you have to, let's suppose, do it for one step. So previously I have not told, I have just given these equations. So this over here is your forward pass. These two things happen. So at each of the layer, so you take this WK, you multiply it with what was previously there, and then you add bias to it. You will get the aggregation, basically an affine transformation. Then on the affine transformation, because that is a linear, that is transformation linear affine. So you have to apply an activation function on that so as to get non-linearity. So this is what you will do. So let's suppose you have input like this. So you have input H0, that is equal to x1, x2. This is how usually input, if we have input which has let's suppose 2 data points. And now second thing is we have to have some hidden layers. Consider we have a hidden layer A1. Now I won't be making this network again and again. You will have to, like, this network is just for the visual representation, but in practice this is how you will write this. You will write the code in this. This is how the mathematics also represents it. So the better picture is to get a very good hold of these things. So H0 is equal to x1 and x2. And now at A1. So A1, as you know now that, so this is the pre-activation between the input and the first hidden layer. So how to do that? So you will have one matrix associated with this, because from the inputs these inputs will be fed into this network. So this W1 H of 0 plus bias. So this is what will happen in the first. Let's consider W1 to be like this. Say W1 is something of this sort. Because if you have very good grip of this, it won't be difficult to code the backpropagation algorithm. Otherwise, you will find some difficulty. So you have W11, 1, W12, 1, and W21, 1, W22, 1. So this is how the matrix. Let's also write the bias matrix, or bias vector rather. So B1. So here we'll write B11, B12. So this is corresponding to the first layer, basically what is in between these layers. So when you give this input, so this is for the first hidden layer. So now after this, you will have to compute this H of 1. After you will have to activate these things. Consider this activation function to be a ReLU function. You can consider it as a sigmoid function, whatever you have. And the definition should be given. So this will be f of a of 1. So this is how I wrote over here. So f of a1. And if it is suppose a ReLU function, so ReLU function is defined something of this sort. Max of a0 of a1, whichever is max. So you will take that value. So this is the definition of ReLU function. Rectified linear function. Okay. So this is how we do it. And then let's suppose now there is an output layer. So this was our step 1. So step 1 was our input. So this was our data. Okay. And this was our step 2. What I wrote in between this is our step 2 on the first hidden layer. So this is step 1. So this is step 2. And you can add a lot of these step 2s. You can add more hidden layers so that you get some output. Let's suppose now we have an output layer. So in output layer, what you can do is you will have to have some separate activation function. If the task is a regression, it can be classification. So how to do that now? You will compute A2 basically. So A2 will be again W2. It will be a matrix W2, and then you will multiply it H1. So what came previously, and then this bias 2. And again, this H2 will be equal to activation of 2. You can keep it like this if it is a regression, because in regression you will just use the affine transformation. You will not apply any activation function. Or if it's a classification task, so you can use softmax or things like that. So this is one of the examples. Is it clear, everybody? Let's take second example where we'll have some input. Say we have input. So input will be like this. So this is the abstraction of the thing. So whatever you have to think from now onwards about neural net, this is how you should think. So first thing, you should have some input. So input will be x, that will be of some dimension. Let's consider this as 3-dimensional input. So usually suppose in natural language processing, the input will be very high dimensional input, say maybe thousands or hundreds of dimensions of input, and this might be input. Then you will have to think about the architecture. So how should our architecture be? So depending on that, you will derive an architecture. So here I'll keep the architecture again simple. So let's suppose I have hidden layer 1, hidden layer 2. I'll have hidden layer 1, hidden layer 1, and hidden layer 2. The second thing I have to decide is, so how many number of neurons should be there? Okay, so what I can do is I can say the hidden number of layers, suppose, is 1:4 neurons. Okay, from 1 we'll go to 4, and then let's suppose here we'll have 2:3, something of this sort. You can control these neuron hyperparameters. So here these are hyperparameters. I should not give any number because I don't know in the example what is coming. Parameters. So you'll have to decide on these things because input will be given to you, and this also is your hyperparameter. How many number of hidden layers? Okay, number of hidden layers. This is again hyperparameter. You have to choose this. So this all comes in the architecture. So you have hidden layer 1, hidden layer 2. So suppose here you again have to make decision. So in this hidden layer 1, so what is the activation you can use? Because you can use different activations for different layers. So let's suppose you decide you will use ReLU here. You decide you will use sigmoid here. Or sometimes usually you decide that in the whole network will only use sigmoid layers, but it's not. You're not being constrained by just one function. You can just make separate networks and decide what functions to use. It's all up to you. Okay, let's consider this. You have input, and then there are a lot of hyperparameters to adjust how many input neurons, how many output neurons should be there. And let's suppose you are also having at the end an output layer. So output layer is also there. Okay, and if it is if it's a classification problem, let's suppose you can have just one neuron. It can be high or low. If it is some say regression problem, you can again have say one neuron. It will just give you one output. If it's some sort of distribution, so you can have those many number of neurons, as in terms of natural language processing LLMs, we saw that there can be a lot of neurons, and then we apply softmax function on this. This again this is problem dependent. So how to decide on output layer? So this is problem dependent. And then you also have to see what activation to use, what output activation to use. Let's suppose now in this input, if input looks like this, so h of 0 always will represent the input like this. So input will be x1, x2, x3. Consider this as an input example. Okay, so this belongs to R3 in this case. So each input example will something look like this. And then what will be happening at the hidden layer first? So you'll compute A1. A1 is W1 H0 plus bias. Okay, so you are free to set this weight and bias because that's how you will learn. And after this, you will apply an activation function. Now, if you see W1 matrix, so W1 matrix will be, suppose if you have if you have some certain examples, if you had say if you write W1 of this sort, so you had 4 examples, suppose. You can, but though it depends how do you decide on this, because the problem is sometimes people write W transpose and W, it doesn't matter. Sometimes people write each data point like this. So let's suppose we have data point this x1, so they'll write x11, x12, x13, something of this sort. Or they can write data from this like this, x11, x12, x13. Okay, so it depends how do you choose the notation. Okay, so depending on that, you can also have different dimension. So if let's suppose you have this in hidden layer, you use 4 neurons. Say suppose you use 4 neurons and you use 3 neurons over here. So now based on this, you will have these W matrices, W and W1, W2 matrices will have values according to that. Okay, let me show you that. So let's suppose if we chose values in such a way so that this W1 matrix, this weight matrix, has dimensions 4 cross 3, because if you know each point has, now each of this point, if you see, is written like this, because it has 3 columns now. So it has 1, 2, 3 columns of this sort. So because we had 3 features, so each of this data point is written like this. This is data point 1, so data point 1, and then you have data point 2, and then you have data point 3, and then you have data point 4, something of this sort. Each of this is now a feature, because each data point might belong to here it belongs to 3-dimensional plane. So we have the columns representing data. So the representation will be, if you are given data points, suppose our data points are maybe x1, x2 and x3. Okay, I'm using superscript and subscripts here. If you see, these were the features which I just mentioned over here. So it can be something of this sort: x111, x121, x13. Maybe I can write it like this. This is the first data point. For the second data point, suppose we have 4 data points, and then we'll write it x second, x2 1, x2 2, x2 3, and so on. So this is how I'll get a matrix. I'll get matrix of this sort. Okay, so that matrix I can call like input matrix. I can call it data matrix. Okay, I can call that as a data matrix. And now if I have to construct this might be my data matrix. So if I have to, this is my data matrix. But after this, I'll have to give this input to this. Rather, this W1 should not, this is not that much. This is the matrix which is before the first hidden layer, between the input and this. So this is our data matrix, and then we'll go to this W1. This W1 is not this matrix. So this is data matrix once we construct data. So now let's suppose this W1 belongs to, say, R 3 cross 4, 4 cross 3. So how will this be computed? So this will be computed based on this. So if you have some neurons over here and if you have some neurons over here, so the matrix in between you can compute based on this. Okay, it usually is the reverse of this. How do you represent it? It depends how do you represent these numbers. So how do you represent this? So you'll again give the dimensions according to that. Okay, after that you will have to apply this. So you compute A1 based on whatever matrix you had, whatever inputs you were given. Okay, you can give even a matrix of inputs also, and then plus then you will have the bias also. And after this you can apply activation on this. So you'll have H1, so that will apply, let's say, ReLU of this. So you'll have ReLU of A of 1. But do keep an eye on these W's and maybe on these X, because if you do some problem in, let's suppose, hidden layers, or you had some problems with weight method, you had some problem with bias, that will propagate throughout. So that's why you have to be very careful with this. Okay, and similar, this again will happen with this. So if I give you an, let's say, I will not do this now. So at your home, what you can do is, so let's suppose if I give 10 neurons over here, if I give, say, 5 neurons over here, if I give, let's suppose, some 4 neurons over here. So you have to compute in this, you have to compute W1, W2, and let's suppose output also, what are the dimensions. So you can lay out this whole network. Here it will take me a little bit of time, so it is better you do it on your spare time, and I believe that you should be able to do it, to just construct W1, W2, H1, A1, something of that sort, and then see output. And let's suppose if you now decide you can use, here you will use, let's suppose, softmax activation, you'll here use softmax activation. Let's say here you'll also use softmax, suppose. So can you sketch out the whole thing? Can you do it on paper, not just creating some network? Because in PyTorch you'll just write some code, then import torch and do this, and you can easily get how many parameters and this, how many parameters. The best exercise would be to do it one by one, to start it from input and see, I have data matrix of this sort here. Let's suppose I had 4 examples. Okay, I had 4 examples, let's suppose n examples, or n data points. So m data points were there, and each had 3 features. So how will my data matrix look like? So it will be x1 3, and this is m cross 3 data points. So each of the row will be, and then you have to construct this W1 based on, so these two things will be based on the number of hidden neurons here. Okay, and you tell them you can even do it by hand. Then forward pass, you can assign some random values to these W's, and after this do the multiplication and go with this. So this is your H0. So this thing over here is your H0. This is the data matrix, initially the matrix that you have, and then you'll perform the multiplication with W1, the matrix which is in between the input layer and the first hidden layer, and then you will have a bias vector which you can again initialize, and it will also have dimensions. So play with these dimensions, highly recommended. So okay, suggestion over here. So whoever will be watching this video, so in the interest of time, I won't do the whole sketch myself. So what you can do is you can stop the video over here, and you can compute W1, you can compute this W2, because we have 2 hidden layers here, and then you can also compute H1, you can also compute H2, and then activations also. Before this, you have to have you have to have these non-linear affine transformations, and then you can, rather, linear affine transformations. So then you can apply H1 and H2, then also you have to compute output, basically HL in this case. So keep in the view that you also have to compute dimensions of everything. So also have in the view that I'll compute dimensions of all these matrices so as to see if the numbers are matching up, and then you can also apply softmax on this, or maybe take a small example than this. Start with small example and see if you can do the forward pass by hand. If I give you example of this sort, say I'll give example like this. I have data point X, so X1 is my first data point, x2 is my second data point, x3 is my third data point. If I give you numbers like this, 0.1, 0.4, 0.8, okay, 0.2, 0.3, 0.6, 0.4, 0.3, 0.1. Suppose it's a classification problem. Say this is 1, 0, and 1, something of this sort. It's a binary classification problem. So if you are given these labels and these are your inputs, and if you are asked that you have two hidden layers, okay, so after the input, so you can decide on these hidden layers and then do this exercise and apply softmax function on this, so that you can perform the forward pass by hand. Here, if I perform forward pass by hand, it will take me maybe more than half an hour to do that. Any questions on this? Till here, is everything clear? This should be crystal clear. Why? Because this is the notation we'll be using throughout, and probably this will be the notation which we will be using while we are coding these algorithms, so as to implement a neural network from scratch by just using maybe NumPy, or we can we can even use lists. We can just truncate NumPy as well. Any questions? So once you are done with this, once you know how to perform forward pass, and then you will have to do loss computation. This is where the story gets interesting now. So you have to compute loss. So if you are not paying attention till now, it's all right. Maybe you can revise it a bit, because there you just had to take care of these dimensions and notations. Now this is the real deal. You have to compute loss now, and we had a huge discussion about loss. We had, I think, a couple of lectures on just loss functions, and now how to compute loss. So based on this, you have to have a divergence function. So if it is a regression problem, you will select your loss function or divergence function accordingly. If it is the classification problem, you will again select your divergence function, something of that sort. But last, let's suppose consider that we call that as yt, okay, or we can call it yt, something of this sort, or yi, however you like it to be. So I'll use yt over here, and then this yt is the prediction of that. So this is our ground truth, and this is our prediction. Okay, and this is your, again, parameter, the way you decide. It's not a parameter actually. So this thing is your choice. So what functions should you use? So now you have to compute loss for one thing. So you'll compute it for all the points. So I'm labeling it here a t. So I can sum it over all the points. So this t goes from 1 to, let's suppose, some capital T points are there, and you will compute loss for this. This is how you will compute loss. And this t over here is total training examples. Okay, and this divergence function is the desired. So this is the desired function, or the loss function you chosen loss function, and it depends on the problem that you are doing. So this is ground truth, this is your prediction value, and this is what is this doing. So this is summing it all, and we can take average. So usually people take average of this, they don't just sum it up, so they'll take average. So this over here is taking average. Okay, I hope this loss is pretty clear. So there is nothing, no problem with this. Now the problem is we have to find if this loss is more. So is there a way we can decrease this loss? So that's what our main task is, to somehow decrease this loss. So that's our job. The goal is decrease the loss. That's why we need loss computation. Once you compute the loss, now you are saying, oh, so you have, our loss is this much. So can we decrease this loss? If we can decrease the loss, and we can show that our sort of model is learning something. Now how to learn that? How to sort of find the ways in which we can learn that, in which we can decrease this loss. Now for that, you should know a bit of calculus, because you know that calculus is the tool by which you can, if you are given some function, you can perform, you can apply derivative onto that, and you can get, let's suppose, some local minima, and you can equate it to 0, and then you can see if I nudge something by this. Okay, let me just go a bit towards this calculus, so that I'll give you the refresher to think about these things, and how can we basically find these values, so as to see how can we do the backpropagation in an effective manner. Suppose you have this function, you have a function y which is equal to f of x. Okay, so this is the function. So in the neural networks term, this function won't be just a single variable function, it will be a multivariate function. You'll have a lot of variables. So we'll start it here, and then we'll slowly go to a multivariate function also. So consider this. So if I'm telling you this, if I'm making some slight change, so x is somehow related to y. Many of you people might know this, so I'll just give a different perspective of looking at this, so that whenever you see these things, this is the picture that pops into your head. Okay, we'll make computation graphs from this. So this is x, and this is y. And y here, if you see f of x, if you give some value to x, and this will give some value to y. So if I make some change in x, so delta x, so it will, some change will be made in y. So I can write it something of this, or wx is somehow proportional to wy. It can be inversely proportional, direct proportional, it will depend, we can change that. And if I can change this to a constant, I'll say wx, say if I write some value over here, some maybe, if I can write x of x doesn't look good, maybe z. of delta y, something of this sort. So this z term over here is derivative. This is how a derivative is defined. So we have seen a lot of perspective on derivatives. So this is how you can write it. So you can say delta x is equal to, if I write derivative now by dy by dx multiplied by, this is delta y. So if there is some change made in x, so there will be something happening to y. So which quantity will tell you that? So this derivative will tell you that. So you have to somehow look it from this perspective now. So small change in x will perform some small change in y. Okay, so if you, this is rather delta y, not delta x. So I should be writing delta y over here and delta x over here. Okay, so if you make some nudge in x, so something will happen to y. Okay, so again, this should be reversed over here. So this is delta y, because we are computing change of delta y. So how much will delta y change? Okay, so this picture is right. So something will be done here, some change will happen over here. So what change will be happening? So if you are doing something of this sort, so something will be multiplied, divided, whatever. So this quantity will be there. It will give you the value of delta y. Okay, so I called that quantity as derivative, and we represent that with by dy by dx. And we had a proper course on calculus, but here I just wanted to see you this notion. So if you make a small change in here, so this is what will happen because of that. And now we'll have, these are called as influence diagrams. So I'll be making diagrams of this sort. So these diagrams are called as influence diagrams. So consider this as, let's suppose, one neuron. You have one neuron, and one neuron will have an impact on other neuron. So that neuron will look something of this sort. Say this is neuron n1, this is some neuron n1 2, and this is some neuron less n1. This, suppose something of this sort. So one neuron is influencing other. So there will be a lot of things will be happening. So we will keep on these pictures. That's why I'm giving a different perspective on looking at looking towards these derivatives. Okay. So these influence diagrams, keep them in your mind. So I'll just make them as notes, so that we'll just extrapolate it to the neural networks. Now I'll take this example. So I'll take a multivariate case. If I have now a function, so initially I had just one function. I had function which was univariate. So in that I had f y is equal to f of x. Now what I can tell is I can take multivariate case. I'll say this y is equal to f of x1, x2, and so on till x suppose m. So these many values are there. So how to do this now? So we cannot now compute just a change. So if I make a diagram of this, if I make influence diagram, how to make influence diagram? So I'll say x1, x2 till xm. So if I change these things, so they'll have some impact on this y. This is how I can make this diagram. Okay, so if I write this, so if I change this x1, so it will have some impact on y. If I change this x2, it will have some impact on y. And we also learned about partial derivative. So if you are having a multivariate case, there we don't take just derivative, we'll take partial derivative, because we'll keep all others constant and we'll take derivative with respect to one thing. So if I just relate these two things, so if I say delta y is equal to some derivative and this delta x1, okay, I can compute partial derivative. I can say delta y is partial derivative of this. So as we said, dy by dx. So here we'll write dy by dx, dou y by dou x. This is how it's read, delta x1. Okay, similarly, this delta y also is related to delta x2. Change in x2 will somehow impact delta y. So we can again write partial derivative of this sort, dy by dou x2. Okay, and so on. So in order to make this influence diagram, I'll just write these things above these. So this will be dou y by dou x1, dou y by dou x2, and this will be dou y by dou xm. Any questions still here? So now if I change this to delta m, so I can write it like this. So delta x1, if I change something of this sort, so it will have an impact on delta y. And similarly delta x2, this will have some impact on this. This is delta x m, this will have some impact on this. And now how to compute the total? How to compute this total basically change in these? Because I have the ability, because this is a multivariate function, I have ability to change a lot of these. I can nudge a lot of these values, a lot of input values. So what I can do is I can apply summation rule over here, because this is going towards the whole same input. So I can write something of this sort. So this dy by dx, let me just exactly see the value. So I can actually write this delta x1, and then this is dou y by dou x1 plus delta x2, dou y by dou x2 plus, and so on, delta xm, dou y by dou xm. This is how I can write the total change. So this is total change in y if I change x by a little, delta x1 by a little, x2 by a little, and xm by, if I nudge all the parameters, this is the total change that will happen. Any questions still here? Now the first thing is we took a univariate case. We had y is equal to f of x. So there we nudged x and we got y. Second case was multivariate case. We had inputs which we had multiple of them, and if we nudge any of these or maybe all of these, some of these, so we can compute what is the total change. Similarly, if you have a nested function, you have something of this sort, y is equal to f of g of x. So what do you do in this case? Okay, so you have something of this, or x is dependent on g, this is dependent on y. So you want to see if I nudge something. So if I nudge delta x, so how will this delta g be impacted, and how will this delta y be impacted? This is what you want. Now we know this. So if you change, suppose if you change delta g, and then you will go to you'll do something with delta y. So how are these two quantities related? So these quantities are related by dy by dg. This is how these quantities are related. So how can I write it? Delta y is equal to dy by dg multiplied by delta g. This is how these quantities are related. Okay. Similarly, how are these two quantities related? If I made some change in x, and how will the g be impacted? So how are they related? So they are related by this. So this is dg by dx. Okay, so in this case, or we can write partial derivatives if it's a multivariate function. So here I'm just taking a univariate function, but it is this is composition of functions. These functions are nested functions, or we can write as composition. So they are nested or composite functions. Okay, so this is where the backpropagation lies. So you'll be having something of this sort. You'll be having some input which will be impacting something, so that will be impacting your loss function. It will be a chain of your functions. So that's why here, if you see, this delta x is related to this delta g. How? So they are related by this. So this delta g is related to this delta y. So how are they related? They are related by this dy by dg. So if I have to compute total change, delta y. So how can you now compute total change? So you'll compute total change something of this sort. You'll see, you'll first relate these two terms. You'll say, okay, if I relate this, if I say dy by dg of this delta of g. Now you know you can compute this delta g from these two things. Okay, so you will compute. So if I write one equation of this sort, so let's suppose one equation is this. So how is delta y and delta z related? So I'm basically writing this equation over here. So if I write second equation to make it more clear, I can write something of this delta y, or delta x rather, here in this case this delta g, this is equal to dg by dx delta x. Okay, so what I'm doing is I'm taking this portion over here, so I can relate it with this. Consider this is not there. Okay, if I can just mask it, I'll have delta g is having some effect on delta y. So how I can quantify that? So delta y is equal to dy by dg multiplied by delta g. And now if I can just truncate this portion, I know how are these two things related. So delta g is equal to this. So if in this case, this is equation 1, this is equation 2. If in equation 1, if I substitute the value of delta g, so what will you get? So delta y is equal to dy by dg, and then you are substituting these values. So you'll get dg by dx delta x. Okay, and this over here is the derivative. So if I now write how are these things related? So how is dy by dx related? So I can write, so they are related by this. So this basically is showing me how is this delta y related to dy. So this is related by this. So I can write directly like this, dy by dg and dg by dx. So this over here is chain rule, which you people have seen earlier also. So this is chain rule. Any questions still here? Isn't it very nice to see it like this? The third and very important case basically is if now your function is such that it takes input as functions itself, and those functions take input as input variables. Suppose you have this f and you have this z1, z2 and so on till zm. But here I can define this zi. So this zi is g of ix. So these are different functions. So if I have to make inference diagram for this, how can I make inference diagram for this? So now you have functions, you have variables, you have a lot of things going on. So you have this x first. So this x goes to all these functions. So it goes to gi of this. So it also goes to say g1. It also goes to g2. It goes to g3 of this and so on. And let's suppose gm of this. So now these things aggregate. These things then are transformed by this f. Again, a function is applied so as on this so as to give us this value y. This is how this x is related to y. Now you can see this exact looks like neural networks. So if you take a neuron, okay, and there will be a lot of outputs going to different neurons, and somehow if you add more of these things in between, you will have a loss function somehow like this. So this will be loss. So this is our input. These might be our hidden layers in between. So but in general, this is the template you will see. So now we'll deal with this portion. So we'll deal with this portion first. If you have these z1, this is your z2. Let me write this in brackets. This is z1, this is your z2, and this is your z3, and this is your zm. So if I have to relate these z's with this y, so if I change something in z's, if I do some nudge in this z1, so what will be the effect on this y? So I can relate this delta y and this delta z, this delta y and these delta z's. Okay, if I just look for one thing, okay, because we did earlier, so this will be summation later on, so we'll do it for just one. Let's suppose z1. So here, how will these two be related? So delta zi and delta z1 and delta y will be related by, like suppose, dou z by dou y. Okay, something of this. So I can write dou z by dou y. So for one example, this would be z1, z2, and if I write it in general, so this will be zi. So now I have to sum them all these things. So if I sum them up, so this will be summation of I goes from 1 to m. Keep this as equation 1. This is going from here to here. Now I have to see how this x is related to all these functions. So if I say how this delta zi, so if I take one function now, delta zi, how is this related to this delta x? If I make some change in x, so how will this delta zi be, how will be zi impacted? So how I can do that? So I'll say this will be equal to dou z by dou x. Okay, because x here is constant, so I can write this as equation 2. And now we can again substitute the values. So you can see, substitute this value delta zi into this. So what you will get? You will get the total loss. So you will see total change rather, not loss. This will be equal to summation of I goes from 1 to m. So this is dou zi by dou y and then multiplied by. So this is delta z1. Delta zi is equal to dou zi. So this should be I over here. So delta z dou zi by dou x, and this is delta x. If you have understood this, so this is what will be happening in the backpropagation. Okay, is it clear so far? Okay, then if this is clear to most of you, so what you can expand this over, you can form a big equation of this sort, and then you can again add more hidden layers in between, and then you will calculate how is one contour related to other. So that is the, what I can say, we said heart of deep learning is backpropagation. Heart of backpropagation is chain rule, and we saw how to apply this chain rule. Okay, now you should not forget this. So usually people try to memorize chain rule. If I let's suppose have to compute dy by dx, so you introduce a variable dy by dz multiplied by dz by dx, something of this sort. Okay, you need not to memorize this way. Okay, so rather you should now internalize it. You should be saying, okay, I can make these influence diagrams. So influence diagram, why are they called influence diagrams? Because input somehow influences some other thing, that influence some other thing, that influence some other thing, and at the end the loss is influenced by something. So if I just take one weight, okay, in order to first give the intuition of backpropagation, then we'll do the mathematics of that. So what is backpropagation doing? Okay, so you have this network. Suppose you have a network, so I'll just make network like this now, or I have somewhere I can copy that network. Here is my network. So if I take this, if I copy this network, okay, this is my network. Suppose I am giving some input. Say I am giving some input to this. So this is my x1, x2, x3, something of this. So if I am giving an input and this is doing the forward pass, and you know how the forward pass is done now. So once the forward pass is done, and then I am computing some loss. So when I am computing the loss, let's suppose I am off by somewhere. I am getting loss very high. Okay, so when I am getting this loss as very high, so the only thing is I can see, okay, what is wrong, what is happening inside this network. So why am I doing something wrong? Where is the scope of improvement? So if there is the scope of improvement, I can change that. If I can change that somehow, so that I can reach some loss, I can reach some value where the losses are less. So let's suppose if you see this loss function over here, so this will be output. Okay, so output will be HL. If I go on the hunt, where is the problem lying? So I can say, okay, there is something wrong with this HL, but this HL in turn is somehow we got it from an activation function called that F. So we got it from some output activation function, and that activation I got from, let's suppose, AL. Okay, basically the linear part affine transformation of the last layer. Okay, so from this last layer, because I have to change the values, if I say okay, I have to do some adjustment to this HL. This HL is not independent. So actually I got this value from these functions. Okay, when I dissect it more, so I said okay, so I got this HL from function of AL. So this AL I got from, let's suppose, W, because you know this AL is equal to WL HL minus 1 plus BL. So this is what this is equal to, if you understood the forward pass before this. So I can say this is equal to WL HL minus 1 plus BL. This is what it is equal to, this AL. Now if I ask, okay, why can I change? So I can change this, wait, I can change this. I can make change into this, because this is where I have the control. And I can change this. Okay, so these two things which I am now writing in red, this WL and BL, this is where I can make changes. Okay, because I was on a hunt. Why is my loss more? So I was inspecting the network. I was saying, oh, there is something wrong with this loss function, HL, the last output. So I'm saying, can I do something with this HL? This HL was a product of AL applied. We were applying some activation function on this. So I cannot do anything with the activation function. I can rather change it, and I can't do much with that. So I said, okay, can I dissect this AL more? Yes, I can do WL HL minus 1 plus B. So what can I change? What do I have control over? I have control over this W and biases. Okay, I can control this. Okay, so can I change WHL? No, it will again go something of this sort. So I'll have to, again, this HL minus 1. So this HL minus 1 will be equal to some function. Call that, let's suppose this was F, say L. So this is FL minus 1, some other activation function. Or let's consider this is only F. So now I have to compute this HL minus 1. So this was equal to, I had some activation function on L minus 1. So can I change AL minus 1? No, I cannot. Can I change HL minus 1? I cannot directly. So what should I do? I should again dissect this. I should say F. What was this equal? This was equal to WL minus 1 HL minus 2 plus BL minus 1. Okay. Again, I have only control over these two things. I can change this weight and I can change these biases. So what I'm writing it in the pink is what I have control over. Okay, now if you constantly see on inspecting the network, you can only change two things. You can change these weights and you can change the biases. You can rather change these soft activation functions. But if you have to make network do something with the loss, if you can nudge some values, the only values that you can nudge are these weights and biases. So this is the core thing that you should get out of this, because there are a lot of functions in the picture. So what you can do, you can probably change this weights and you can change the bias. If you keep on going, so at the end you will get H0. So H0 is your input and that input is fixed. You cannot change this. So all in all, what you are changing all these. You are changing from WL minus 1 till W1. You can change this. You can change BL minus 1 till, let's suppose, B1. You can change weights and biases, because these are the culprits which are giving either a good loss or the bad loss. So these are weights and these are our biases. This is what you can change. So on inspecting the network, we cannot do anything with the functions, because they are just, this H is getting an output of activation of something. Okay, activation of linear transformation or affine transformation. So, and that affine transformation, we got it from weights and biases. So we can change weights and biases. Is this clear? Is this picture clear right now? So here, if I categorize this in two things, so I had input as my input is fixed. I cannot do anything with input. Input is fixed. Okay, and then I had something which I can call as dependent functions or dependent parameters. Dependent parameters. So what are these dependent parameters? So these are the parameters which are just the causation. Okay, which just happened. They happened because something happened. They happened as something happened before them. So what are the dependent parameters? These are those activation functions. This activation when you apply the activation function, basically the hidden output, the hidden outputs, comma, and the aggregation. So these also can be like tuned. So we can see that, okay, if we change these, we can have, but they are dependent parameters. They are dependent outputs. So what are the dependent? Or there are something which we can call as independent parameters. So what are these independent parameters? There are only two types in the neural networks. We have these weights and biases. You have weights, comma, bias. Okay, this we usually change. This is what we have control over. So you have control over these, and these things happen, or these things take value as a consequence of this. So there is some cause and there is some effect. So these things show an effect because this caused something. Okay, so this is where we have the control. So independent parameters are the parameters that we can nudge, that we can adjust so as to decrease or increase the loss. This should be very clear into your head. Why? Because sometimes you might have this question that we have weights and biases, and then we have a lot of functions in between also. Can't we change these things? Okay, there is a proper categorization. What? So independent parameters are the ones which we can change by hand, which you can change by backpropagation. But these dependent parameters or these dependent values which we will get, so they'll be as an effect of this cause. So these things produce the cause. So these are the causes, these are the cause, and this is the effect that we get. Okay, and we usually do not worry about the effect. We see what was the cause, why did it come from. So if we can somehow do something to these weights and biases, maybe this dependent parameters will change their behavior. Okay, because that's why we call them as dependent parameters, because independent parameters were the one which we had control over, and these dependent parameters were giving us the values because of the causation of these independent parameters. Any questions to here? Now if you understood this, the second thing that I want you to know about this backpropagation algorithm and from these weights and biases is this. So how to intuitively understand this, what is happening actually. So what is happening is you have a lot of parameters. Consider that you have a vector of parameters. So you have this cost function C or J or L, you have some loss function of this L of theta. So this is L, it takes value some weights W1, W2, something of this sort, and then bias 1, bias 2, something of this sort. So what will happen is we can consider this as a vector. If we flatten this out, so you can consider this as a vector. So let's consider just one neuron. So you have one neuron over here. Okay. And then what you can do is you have a lot of output layers. So let's suppose we are doing MNIST classification, or you are doing cat, dog, let's suppose man, woman, some example, image classification. Suppose you have in output you have 4 neurons. Okay, and you have to adjust these weights. If you see this, sort of thing, so you have to adjust these, and these things will have certain values. So these weights, why are they even called weights? Because there is strength associated with this. So there is some strength. So suppose the value that we got, we gave a picture to this whole neuron. I'm just talking about now one neuron and the output layer. There are a lot of things happening outside. I just want to isolate this thing to make you understand what is actually intuitively happening. So what is happening there is you had, let's suppose this was cat and this was dog, this was say man, this is woman. So this is the classification that you are doing. It is a multi-class classification where these are the images. So now your network predicted something of this sort. It predicted 0.1, 0.3. Okay, and now this is say 0.4 and this is 0.2. But now the actual thing that the image that you gave, suppose this was the image and this was image of a cat. Say this was image of a cat. So when this was given to the network and at the output we got this. So the vector should have been something of this sort, 1, 0, 0, 0, one hot encoded vector, but you got something of this sort. So what is this basically telling? So you have to do something in the network so that this cat goes up, this cat goes up by huge, okay, and this dog comes down, and this comes down a lot more than dog, and this comes down a lot less than dog, a little less than dog. So but this cat should go up by a huge thing. So that you will have vector of something, and you will have to have these weights. You'll have these weights over here. So you'll have some weight over here. You'll have some weight. So this weight will have some strength. So this weight, and this will, let's suppose this weight has some strength 3. This weight has some strength 1. This has some 2. This has 4. So that basically means whatever thing that you do to this, and if you do it to this, so there is some relation with this. So if you do some changes with this, okay, so it will have 4 times impact of this, where you have just 1. That's why they're called weights. You might be having a question why they called weights. That's why they're called weights, because they have strengths associated with them. So whatever change you made to this, so let's suppose you have this one, you made some slight change in this. So if you made the same change in this, if you made that slight change, because this thing has 4 times impact in this, roughly speaking. Okay, that's what you should get out of this. So if this weight was 1, this was 2, this was 3, and this was 4. So if you made some change in this, suppose in this, okay, and you made the same change in this, whatever change you made here, and whatever the same change you made here, this thing will have 3 times the impact than this. Okay, that's why they're called weights. And why? Because there is some strength associated with it. So that there is a theory which is called Hebbian theory, which we also discussed briefly in the history. So neurons that fire together, they wire together. Okay, so this is that thing. So if you somehow make some change over here, so this will give you maybe less output, and this will give you more output, because these things. And how is this coming? Probably this might be coming from some other things. So this weight is more important weight than this weight. Okay, you might have heard about dropouts and things like that. So you should see backpropagation like this. Well, what backpropagation is basically trying to do is, it is trying to see, okay, what change will give you more better outputs. What changes matter more? So if I made a slight change in this, so what will happen? So as I said, if you made some change in here, and if you made same change in here, so this neuron seems to be producing the thrice effect of that. Okay, but depending on should we get it up or should we bring it down, because you know that it's a combination of all these things up. Did you get the intuition? What is why are they called weights, and what is backpropagation? What is the goal of backpropagation basically? So how in actuality how it is happening now? So we'll see that now. So before going into the math, I want you people to understand the intuition behind that and what is happening underneath the hood. So I'm saying now you have to change all of these things. So what is happening? You give one example and you are computing this vector. You are computing a vector which is telling you, okay, you adjust these weights and biases. So this will be a lot of network will be, so the huge network will be there. So there will be a lot of these weights and biases. So if you compute this for one image, so you have, let's suppose, data point 1, image 1. So you'll be given this delta W1, delta W2. So this will be telling you how much to nudge these things. But you cannot do it for every example because you have millions of examples. Okay, suppose you have 1 million examples. You have to give one example, and then you will compute this W1 correspond to 1. So basically what I mean by this is how much to nudge based on this input image 1. So input image 1 is telling to try it. Okay, this cat value should be higher. So input, let's suppose, second might be dog. So this might be telling you, no, you do parameters like this. So what you basically try to do, you try to average it out. You try to take an average. So you give one input, you compute these, how much to nudge. Okay, you give second example, you again try to compute what should be the value, how should be this W1, 2. So this is second image. Okay, when you give second data example. Similarly, when you give third example, so it will try to tell you to change this W1 by this third example, because all of these examples will try to make their network learn themselves. Okay, so if I am having one image, if we had just one output, you can just pass it again. Okay, and it will tell you, okay, change this. It will try to give all the probability to the cat. It will try to make the neural network sort of over represent this cat. So whatever example now it give, it will say, okay, this is a cat, because it is giving high probability distribution to this cat if this was just one example. So why are you giving a lot more examples? Because it tries to compute all these gradient vectors. So these vectors will be called as gradient vectors. So they are all gradients. So one example will give one gradient vector, second example will give second gradient vector, third example will give third gradient vector. So what do you do after that? You take average of all of these. So you will take this all these gradient vectors, suppose this is Wi, and you sum them and you divide it by total examples. So how many examples did you take? So now if you see, we have million examples. So now we have to perform forward pass 1 million times, suppose, and then for each of the example we'll get one gradient vector that will tell you how to change, what change should we make the network. So a cat example is trying to tell you, okay, based on this image, so you should get this distribution up, you should get this neuron, so we should give it more value. Similarly, when second value is given to the dog, so each of the example is telling to trying to tell the neural network that you adjust these values according to this. But what do we do then that? So we average it out. We do not just listen to one example, we average it out. But the realistic problem is if you have 1 million data points. So 1 million data points if you have, then you have to perform forward pass and then you have to compute backward pass for each million points. It will be a lot more computationally expensive. That's why we go to what's called as batching. We do mini batch. So why do we take mini batch? So we'll shuffle the data. We have 1 million points, so you will shuffle it. So once you shuffle it, so you will, let's suppose after shuffling, you will take 32 examples randomly out of that. So once you take those 32 examples, you will just perform forward pass on those 32 examples. Now after that, what will happen because of that thing? So you will get some gradient and you will average out on that, and you will be getting some direction so as to nudge the parameters in, but that won't be the exact those won't be the parameters where you will exactly get the better value for this loss function. But still, because you took these randomly, so along the way you are thinking that if I just take these 32 examples, so I'll get some direction which will be a little bit right direction. So it is basically trying to navigate that terrain, basically trying to navigate that manifold. So if you are here, it will give you some wrong direction, but that wrong direction won't be much. So it will be like a drunkard person navigating the that terrain. So if you understood this example, why don't we do with one example and then update it, one example then update it? So it will be computationally very expensive if you just give it perform backpropagation update, one example perform backpropagation update. So it will be computationally expensive. So in real world problems or in real neural networks, when you code it up, so what do? So you give some batch of this. So where you do this, so you might have heard about SGD, stochastic gradient gradient batching algorithm. So how is it happening? Because you give it you give it a real shuffle. So you have 1 million points, you shuffle the whole data. So after that, you took randomly 32 points. That's why this stochasticity came into the picture, the probabilistic algorithm came into the picture, and then you applied gradient descent on this. You accumulate those gradients and average it out, and after that you applied that to net. You applied those changes to network. Otherwise, you would have applied by each example, and that is not computationally feasible. Or it might be, but it's not practically done. Why is it not done? Because you don't have that much computational power to perform it on first point and second point and third point. That's why you rather use batches of this sort. Is it clear? This is what backpropagation is doing. So all in all, now what is backpropagation trying to do? If you see this, So backpropagation is trying to give one data point, it is performing forward pass, and one data point is telling the network how to adjust these weights and biases, because corresponding to each point you will get a gradient vector. You will get a vector of these gradients which we will call as gradients. So we get a gradient of, rather than you will get vector of these derivatives which we call gradient. So you will get this gradient, and after that you will say, okay, I make these adjustments in the network. So you don't do it immediately because you might have 1 million points. So what you do is you do it for 1 point. So that 1 point is in the network, okay, adjust in this direction. Okay, and then you take it second point, first point, second point, third point, fourth point. You keep on calculating these gradients, and after that, what do? You average it out. Otherwise, there is a problem. If let's suppose one point told you, okay, do this, and you made those changes, and then you did it second time, that second time can undo that change, can undo those changes. So we want to do what should we do at average? So what should be done at average? So this is what companies do. Let's suppose if you are going to a company, how much CTC are we giving at average to the candidate? They won't just check, okay, one candidate we're giving 50 lakhs, second candidate 30 lakhs, then third candidate comes, give him 30 lakhs. Also, no. So on each they'll compute at average, because we believe in probability, we believe in law of large numbers, that it will somehow stabilize after a while. Okay, that's what we do. Give 1 point, compute its gradient. Second point, compute its gradient. Third point, compute its gradient, and then average out all the gradients and make the change in the network. But it's not feasible to do it on 1 million points altogether. So what do? We take mini batches in this. So we take mini batch. So mini batch of 32 points, 128 points. But it's very good if we can do it 1 million points altogether, because that will be giving you a better average. Okay, but rather than that, you just shuffle the data. You shuffle data and you then randomly sample. Let's suppose some mini batch of size 32, 64, 128, something of this sort. Okay. After this, based on these 128 points, based on the 64 points, so you compute this gradient, you compute these derivatives, and you compute a vector of these derivatives, that's called gradient, and then you do those changes, and then you apply gradient descent on this. That's why this is called as SGD, stochastic gradient descent algorithm, because this is a probabilistic thing. You shuffle it and then you sample it again randomly out of that thing. And we just did a small calculation that there are hiccups possible, but the those probability of happening those hiccups is very less. So this is what backpropagation does in a nutshell. Okay, and then if you got this intuition right, we'll have to see the mathematics behind it. So can I assume that you people got the intuition right? So this lecture will start with just a revision of these notations. Okay, so if you see all of this, so this is my input layer, so where k is equal to 0 and layer number is 0, and this is denoted by h of 0, that is this x, if you can see over here. If I can zoom it a bit and you can see it over here. So this is my input layer that you can see. I have made a neural network over here, and these are two hidden layers. Okay, and each of this is denoted by, and you know that here we have, let's suppose, if you see this, I can write this is A1. Similarly, I can have A2, A3. I will write A1 like this, A in superscript, so that it corresponds to layer. So this will be A11, because we have pre-activation. This A11 is a pre-activation. After this, you apply some activation function on it, you get this H11. And similarly, for this, let's suppose, after this will be A2 and this will be H2. So this is your pre-activation and this is your activation. Okay, and all of these things are written over here. So do pause the video to see it. So you have weight matrix and you have this bias, and each of this weight, if I have to write this weight, this will be W111. So it belongs to weight matrix 1, and it connects us for first neuron, the first input with the first neuron or the first layer, first hidden layer. So if I have to write this, let's suppose, what will be the weight of this? This will be W21. So first input now gets connected to second neuron. So this is written as W21, the way I wrote it here. Okay, so I have written all the notations over here. So if you see this, these are the key notations. So you have NK is the number of neurons in the layer K, and this F is activation, AK is pre-activation values, HK is post-activation. Okay, I hope that this is clear. So now this thing I can remove it from here and I can go back to my normal screen. Okay, now if you see this, so we have learned this. So we will have to apply backpropagation on this. Previously I told you the essence of backpropagation. Backpropagation is an algorithm by the help of which you train a network. So I also told you what's the meaning of training. You have these parameters theta, in which you have these weights and biases. You have weights and biases. So, and you have to somehow, you have these parameters theta, in which you have these weights and biases, which you try to adjust. Based on that, you try to actually, you are navigating an error surface, and you want to reach that point where the value is minimum. So how to navigate? You saw that we have to navigate by using gradient descent. And now you should get a direction where to take steps, and you saw that we have to compute gradients. Now we'll see how to compute those gradients and how to do this with a real network. Okay, so you will have your loss function. Okay, you have some loss function of L. which takes some parameters. Let's suppose the parameters are used these W's, W1, W2, bias 1, bias 2, bias 1, bias 2, and so on, and it gives you certain value. Call that cost. Let's suppose it gives you some cost or some loss, so we call this as loss function. So based on this loss, we have to optimize the parameters. So first thing, you should know all these things about, you should know all of these things in order to understand the backpropagation algorithm. Okay, you have to somehow know all of these things. So I hope that at least these things are clear for you. So in the first thing, what do you do is, we have also rehearsed a bit about calculus. So you saw that we saw how actually one thing is impacting other things. So we saw somewhere if you have x and if it has some dependency, or the y has dependency over x. So how are these things dependent? If you want to optimize this, what can you do? You say that these things are connected by, it's about dou y by dou x is how you calculate them. And then we saw that if we have x, y, z, and z, and we also saw that. I think it's all covered in the previous lecture while we saw all of these things. And now today we'll see backpropagation. So in order to introduce backpropagation, now the mathematics behind the backpropagation. Give me a second. So we're discussing with this. So in order to understand the backpropagation algorithm, you should know all of these stuff. So you have to optimize loss somehow. Okay, now before going to these things, I will start with very basic stuff. So let's suppose you have an expression of this sort. You have, say you have this L is equal to A plus B multiplied by C. Okay, so this is what we actually do in the neural net. If you see your neural networks, that is nothing but function of function. There's a composition of function over here. So here let's consider these three things. So you have some parameter A, you have some parameter B, and you have some parameter C, and they are, we're adding A plus B and then multiplying the C, and then we're computing this loss. Okay, now let's suppose you can adjust these things in order to get the least value of this. So you can see that this is the function. So L takes values of A comma B comma C, and they are related with this A plus B multiplied by C, something of this sort. Okay, and somewhere it will take the least value. Okay, here you can easily say, you can give some negative positive values here and there, and you can come up with the least value somewhere around there. So now if you see this, I can make a graph out of this. I can say this, you have this A, and then you add it, you have a node A, suppose. Okay, and then you perform certain operation on this, and then you have this node B. These are values, and it produces, let's suppose, something which I can call, let's suppose E. Let's suppose some X or AB, I can call it node AB. Okay, and then this AB, it gets another node. Okay, and we multiply these things together, and you get, let's suppose, C, and you get output as A multiplied by A, B, and C. I'll write this. Okay, and let's call this L, the L that we have over here. The thing that I made over here is called as a computational graph. This is called as a computational graph. Okay, this is what we'll be implementing once we implement these things in our library that we want to make, the library for the neural networks. So we'll basically make these computational graphs. So we have some nodes A and B. Okay, and we have a node, let's say plus node. So we add these things together, and then they produce AB. Okay, and then we multiply it with C, and it produces some loss. Now we'll have to see there is some value for this loss. Now I will see if I tweak, let's suppose, this value C, or if I tweak this node, if I tweak nodes AB. How can I tweak nodes AB? I have to tweak node A or B. So consider intent setting of neural network. So you have loss function that is dependent on some activation function. That activation function is dependent on some aggregation. That aggregation is dependent on weights and biases. That's what is happening over here. So if you have to compute, let's suppose, how nudging this value will impact this. Okay, so what you will do is you will compute derivative of this. You will see dl by dA. That's what you have to compute. The partial derivative, because you know the L is, you have an expression of this sort, but in neural network it will be huge expression. Now you have to compute this dl by dA. So if you see this previously from the refresher of calculus, you know that how to compute this. So this is being impacted, this L is being impacted by A from here, it goes till here, it goes from here. So this is how it's being impacted. So you will now see, okay, this L is being impacted by this AB. Okay, so how is it impacting it? So we can say dl by dab. So this is that node. This is getting impacted by this, but this AB in turn is getting impacted by A. Okay, if you see this, if you follow this by chain rule, you will write it like this. How is this AB being impacted by A? Okay, then I can compute how is loss function or L being computed, how is it being affected by A. And similarly, you can say how is this B impacting this L. You can say dou L by dou B. So basically, if I nudge this value B, if I do slight change in this, what is the effect that L is having? Okay, that's what we want. So I was talking about this. So if I make slight change in B, if I make some small change in B, what will be the impact that we'll see in L, because we want to somehow get this loss function down. If consider this L as your loss function, you want to get it down. So you can write it in calculus like this. Take partial derivative of this loss function with respect to B. So how to do that? You know that this B actually I cannot compute directly because it comes through a computation graph. It comes through this because this L is being impacted by AB. Okay, and this AB in turn is impacted by B. Again, we can use chain rule of calculus because we have seen that. So how to write that? So you can say this is equal to dou L by dou AB. Okay, how is this L impacted by AB? But in turn this AB is impacted by B. So how to do that? Then you multiply this by dou AB divided by dou B. Again, for this parameter C, let's suppose we have all these parameters, we can nudge these values A, B and C. So how to compute? Now you can see this C has direct, if you nudge this C, it has direct impact on this L. So I can write dou L by dou C. Okay, what is, if I make slight change in C, what will be the impact on L? So I can say this dou L by dou C is like, you can directly compute it. You don't need to even apply chain rule. Okay, for this you can directly compute it, this one. So now I got these three things. I got 1, 2 and 3 things. So if I collect all of these 3 things, I call that gradient. So I'd get dou L by dou A, dou L by dou B, dou L by dou C. So I computed their derivatives and I collected them together. So this is what I call as gradient. And then you know what to do this, because gradient gives you steepest ascent. It gives you like where you can, if you go in the direction of gradient, it will give you the direction where the function increases, but you have to decrease the function. You have to get the loss down. So that's why you go reverse. Then you apply gradient descent on this. So you apply gradient descent after computing these derivative vectors. So you have a vector of derivatives which is called as gradient. So then you apply gradient descent on this. Any questions still here? Now that you understood this, after this we apply gradient descent, and now we will see how to perform this backpropagation. You saw that we can perform it easily over here. If A has certain values, you will get some gradient, and you will just remove these. You will say A minus. Let's suppose if you have to update A, so you will have A new is equal to A old. Let's suppose you had some old minus some eta, some learning rate multiplied by, you have created this, so you will say dou L by dou A. This is how you apply gradient descent. Now we'll have to do the same thing over these neural networks. Okay, consider this. We'll take a smaller example and then we'll slowly go towards the whole neural network, towards the backpropagation, and we'll understand the whole mathematics behind that. Suppose you have this x1. So x1 is the input that you have, and then you have this a11. You have this pre-activation, or you can call it linear transform or affine transformation. You take x and you have this a11. After this you apply activation, you get h11. Okay, after this you will again apply, suppose it's a 2-layer neural network, so this is x1, a11, h11, then you will get a21, then this will be again h21. You will give it some activation, and then at the end till you can keep on going, and you will say I have a huge network of this sort. Let me bring it over here. Okay, h21. After that you can have, let's suppose, some layers, and you will have some al1. Okay, and nth layer you will have pre-activation at nth layer, and after that you will have HL, and finally you will convert that into output. So this will be converted into output, let's suppose some prediction Y, or you can directly use this as prediction. And then after you have this, so this thing along with the original Y. Okay, and there will be some divergence function which will give us loss. This will be giving us the loss function. If I just talk about a network, I am just taking one neuron out of that, so I am taking a single neuron. Now you see this is a computational graph, the graph that I just made. So this x1 is our input feature. Then this a11 is linear combination weighted sum in the first layer. This is the activation in the first layer, first hidden layer. This a21 is the linear combination in the second layer, activation in the second layer. So this is linear combination in the lth layer, and this is the output layer, or HL. We can call this as activation in the lth layer. And then you get out of this, you will apply some activation again. You will get some output because of that. So this output and the ground truth you will have. You apply divergence on that, the loss function, basically you will get loss out of this. And now suppose you have to perform computation on this. So what you will do? You will initially do forward pass. So you will do forward pass. You know what forward pass is? The forward pass basically is you compute all of this stuff. You compute this a11, h11, because you know what a11 is equal to. If you have to compute that, a11 is equal to w111. You take the first weight, and that you take this weight. If I show you the network again, the network that we had, so this weight over here. This is not pretty visible, but I think you can figure it out. So this weight w11, if you take this and you are having this x1, so I'm talking about this layer. So you have this line, this will give you a11, then you have this h11, so you'll go here, you'll go here. So this is what I made, okay, till nth layer. So I'm speaking about this one unit over here. Everybody should be clear on this point. So I'm speaking about this path. I'm going from this path to this path. Okay, I hope this is clear for everybody. Okay, let me move then. Now you have this x1, it goes to a11, h11. Okay, so these are the values. So this is the first layer activation, a11, and this is first layer activation. This is first layer affine transformation, okay, or linear transformation. So now forward pass, how will I calculate that? This a11 is equal to w11 from the first layer multiplied with the x1. Okay, this is how you can get it if you have to take the linear combination. And then you can also speak about bias plus, let's suppose you have this b11. So if I also connect these bias over here, so how can I connect bias? So usually bias is, so a node is there which is given value 1. Okay, a node will be there which will be given value 1. This will be a smaller node, let's suppose this will be constant 1, and all its connections will be given here, 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 here. So this is how bias is defined in the networks. Similarly for this network, again 1 will be given, suppose here 1 will be given here, and then all of its connections will be connected like this. So this will act as bias, because you know those matrix multiplications that we have seen. Now you will do forward pass initially like this. So forward pass, you will have a11, so that will be, you take the matrix, take that w11 and 1, that is the weight, this is that weight, multiply it with the x1, the input, and this plus b11, the bias corresponding to this. After this, this will be the linear combination or affine transformation, the first step. Okay, linear transformation or affine transformation. So in this case, this is affine transformation because it has bias in it. Now after this, we'll do activation. So how to perform activation, I'm showing you on the single step, and then we'll go it over the vector notation. And now we'll have to compute h11. How to compute h11? You will apply some function. Let's call that function ReLU in this case, or sigmoid. Let's call that function f. So you'll apply f on this a11. Okay, and you will get some value out of it. If you have value, suppose you have, this is 0, this is suppose 0.5, this is 0. This, let's suppose 2, this value is 2. So this will be equal to 1.0. And after applying, let's suppose you have ReLU now. So the ReLU basically is max of 0, a11. If you apply ReLU or sigma, it depends on that, you will get still a value of 1.0 over here. Okay, and then you will have to perform second layer, and you know how to perform the forward pass. So basically you store these values. You have a11, h11, h21, you have all these values now. Now this is in the forward pass. After you have this, now what you have to do, you have to compute gradients. So you have to compute gradients such that you will nudge these values. You will get, based on the forward pass, you will compute loss. So after you have the forward pass, you have a loss, that will be a single number. This will be a single number. So what will happen as a corresponding to that, you will see, okay, how good is my neural network. So if the number is very high, you will say that I have very high loss, that means my network is not learning very good, I have to do something with it. Okay, now let's see how to do this with the gradients. The general approach would be, so you let's suppose do something of this sort. You will take, as we did in this, but if you have to perform the backpropagation in the network, okay, the first thing you will do is, you will say I have to compute this dl by d theta. This is what I have to compute. Okay, so how to do that? So dl divided by what was the output, okay, and then multiplied by what was the, how was output dependent on these parameters. So that's what, this is the general approach. So let's suppose you have these parameters theta, you will say I'll take partial derivative of this L with respect to this output, or whatever output I had, and then partial derivative output with respect to this theta, and then you will have to again use the chain rule. Consider this, I'll take a small example, I'll take example of this sort. Let's suppose you need to compute what is d dou L by dou 1 1 1, the first weight. Suppose you have to do this, Is everybody following me so far? Okay, now this is the general setting. So this is what we generally want to do. In general, this is what we want to do. We have a loss function, and we want to compute the derivative with respect to all the parameters. So we'll do it step by step. So you have seen the forward pass. Okay, let's do this. This algorithm can be seen from two perspectives. We can see it element wise, and then in the vector notation. We'll see both the things in sync. Let's suppose you have this aij. Okay, this is how you perform forward pass. You have ai, aik. Can anybody tell me what this is? If I write aik, Mahmood? Well, the first thing that we'll see over here is element wise. So now, so far we have seen forward pass like this. We have ak pre-activation on the affine transformation. This is equal to wk. This is a whole matrix, and then we have hk minus 1, and then we are writing plus bias. So this was in vector form. This is what we have seen so far, how forward pass looks like. And then we said, okay, after applying, so we can apply this. We can apply activation on this. So we have hk is equal to some activation function f applied on f. Okay, but here now we'll see element wise. What is happening element wise? So how is this happening element wise? So each of this ak is the vector. So you know that. So this ak is a vector of this sort. So you have ak1, AK2, depends on how many neurons are there. Okay, similarly this H is a vector, so this WK is a matrix. Okay, and all of these things should be clear. This is a matrix of weights, okay, between K and K minus 1 layer, and this is that activation after activation, and this is bias, or all this is a vector, this is a vector, this is a matrix, and this is a vector. And here when you apply this activation, you do element wise, you apply this on each element. So now we'll see single element of this AK. So if I write that, so I can write AKI, ith element of this. So how to get that? So I'll basically query this vector. So I'll query this matrix. So I have a matrix W of this sort. Okay, if I have a network of this sort, I have 4 neurons in the coming layer, and in the present layer I have 3 neurons. So W matrix over here will be of size 4 cross 3. 4 cross 3. This is how the matrix would look like if we have something of this sort. If we have in the next layer we have n neurons, so n neurons in the next layer. In the previous layer, if we have p neurons in the previous layer, so n cross p. So we write the dimension of n first and then p. That's how we adjust these weights now. So in this we have weights. So now weights will look something of this. So as I said, you will see m cross n. M basically means next layer. Let me write n cross p. N means next and p means previous. Okay. So how to now write this? So if you see in this, so you will have something of this sort. You will have n values over here, n rows. So you'll have n rows and p columns. In order to compute this, so you have this whole matrix W, and then you have a vector H. This H is a vector. You have to compute A. So you will take ith entry of this. You will take ith entry. Consider this as ith entry. So you will fix I value. So this value over here, all these will be WI1, WI2, WI3. This is how we write it. So we'll write WI1, WI2, WI2, WI3, something of this, WI4 until WIM. So this is WI if you see. So what is this I? This I is the target node if we are talking in the neural network setting. So this, let's suppose if we talk about this neuron, if we talk about this neuron, you have this neuron. Okay, we are talking about this neuron. So this will be this multiplied by, let's say x1 multiplied by W11. Okay, then x2 multiplied by W, because it is now going to the first neuron W12. So 1 is fixed. So first I is fixed and then we are changing. And after this, we'll write x3 multiplied by W13 because 1 is fixed. That's the reason we wrote this as flipped. So when I wrote these weights, I wrote it as Wij. This I was from, this was sink, our target, and this was our source. I think we have covered this in the previous lecture. So now this is some ith weight vector. Okay, it below, like all these weights are basically all the weights that come towards a neuron. So ith neuron here is fixed. And now you'll have to come to this AI. So you will do this. You'll say, take this weight matrix, take this K weight matrix. Okay, fix this I, and take all values. Let's suppose J. So J goes from, let's suppose 1 to n, something of this. Or how many values are there? So you have to see according to the value of n over here. So after you do this, you will multiply it with HK. Okay, you have this HK. Now you have this whole matrix, you have this whole value, and you will multiply this with HK over here. So HK, how you have to also have this point-wise multiplication. You will do HK of J. So this will be J 1, 2, 3, 4, and and in the bias. So in the bias, if you see, you will get one value of this. When you perform this and this like this dot product, you will get single value, and then you will have to just add bias. So in that bias also is a vector. So you have this vector, the bias vector. What you will do in the bias vector, you will just take ith entry from that. You have this BK, and it has some ith entry here. So you will take this ith entry, BK, ith entry of this. Okay, so this is the element wise forward pass. So after you have this, what will you do? So in order to get this, in order to get activation of this, you will write HK of J, HKI, basically activation. So you will perform this activation. So HAI of K. So these two steps. So this is applying activation. So this is activation, and this over here is affine transformation. Affine transformation for a point. I'll just write affine transformation for a point. I think this should be clear by now. Any questions still here? I hope you understood this now. So if you understood this, so what we basically have, so after we get output, so let's say H0 is our input, and at the end we get HL. This is our Y. So whole of this can be a vector. So this is a vector, this is a vector. How to write this? So this X could have been X11, X12, this can be a whole vector. And this prediction also could have been Y11, Y12. So this is all prediction. So this could have been this could be the all vector. And then what you do is you apply some divergence function, which we call loss function. So divergence of, so this prediction and the real value. This is prediction is HL in our case, and the ground truth. That's why. and then this is your loss. Call this your loss, and this loss you'll have to you'll have to perform the backpropagation on this. So usually what we do, we cache these AK and HK values. So you have these vectors. So that is why PyTorch is very efficient. Why? Because it does broadcasting. It does multiplication on vectors and whole matrices in one go. It doesn't do element wise. Okay, we saw that in NumPy as well. We saw that in maybe some other pandas as well. They perform what's called as broadcasting. They do broadcasting and they can do these things in one go, not having these parallel threads to do point wise multiplication.